For nearly a century, the Standard Model has served as the definitive rulebook for the cosmos. It consists of a set of equations that has predicted the behavior of the universe from the Big Bang to the present, with enough precision to make it nearly impossible to doubt. The entire framework relies on the Hubble constant, a single number representing the exact rate at which the universe is expanding at this very moment. We calculate this rate two ways. First, analyzing the early cosmic microwave background predicts an expansion of 67 kilometers per second per megaparsec. The second measures local pulsing stars directly, getting 73. This creates a massive gap between our theories and reality. This 8% discrepancy changes the entire history of existence. It suggests the universe is a billion years younger than we thought, shifting the timeline for when the first stars formed and when the chemistry required for life became possible. Astronomers initially assumed this Hubble tension was a simple measurement error. They believed cosmic dust in young galaxies was blurring our view, making stars appear closer and brighter than they actually were. The James Webb Space Telescope was designed to settle this dispute. Its 6.5-meter gold mirror was built specifically to peer through that dust and provide a definitive measurement. Webb's infrared sensors operate with a level of sensitivity that reveals details previously hidden from every other telescope in history. The mission was simple. Webb would either reveal a common instrumental glitch or provide the evidence needed to challenge our understanding of physical laws. Physicist Adam Rees used Webb to look directly at the stars that had caused so much controversy. The data was a shock. Webb confirmed the original measurements almost perfectly. The distances held firm, and the expansion rate stayed locked at 73. Attempting to find a middle ground, astronomer Wendy Friedman measured a different class of stars called red giants. Her results came back at 70, a number that sits awkwardly between the two existing camps. Friedman's findings suggest that the very tools we use to measure cosmic distance, the foundation of all astronomy, may contain internal contradictions we don't yet understand. We can no longer blame our instruments for this mismatch. The universe is expanding at a rate that the Standard Model cannot account for. Webb revealed a second major problem when it looked back at the infant universe. It found massive, structured spiral galaxies in an era where models predicted only chaotic clouds of gas and dust. Scientists initially hoped this was a false alarm caused by little red dots, supermassive black holes that emit so much light they make small galaxies look 10 times heavier than they are. However, even after accounting for the light from those black holes, many galaxies remain twice as massive as the Standard Model allows. These galaxies appear to have converted nearly 100% of their gas into stars with perfect efficiency. In our current models of physics, gas is heated or blown away by radiation, making this level of star building nearly impossible. A third anomaly appeared in the actual shapes of these early galaxies. Instead of the clusters we expected, Webb observed galaxies stretched out into long, thin streams like cosmic cigars. These shapes challenge the cold dark matter model, which predicts a clumpy, rigid structure. These elongated streams align much better with wave dark matter, where particles behave like a fluid, allowing stars to flow in long currents. This matches the S8 tension, a separate issue where direct measurements of the modern universe show that matter is significantly less clumpy than our theories predict. The expansion rate, the premature galaxy formation, and the lack of matter clustering have moved beyond being isolated glitches. Together, they provide a consistent signal that the foundation of cosmology requires a significant revision. The Standard Model continues to accurately explain the cosmic microwave background and the universe's elemental ratios. However, the data suggests a massive, unseen influence likely operated in the billions of years between the Big Bang and the present day. One prominent theory is early dark energy. It suggests the universe received a sudden, violent burst of expansion shortly after its birth, before the energy source simply vanished. This hypothetical kick would change the early expansion rate enough to reconcile the ancient data with our modern measurements, without discarding the parts of the model that still work. Nobel laureate David Gross describes this situation as a productive crisis. It represents the specific moment when observed facts force a scientific field to evolve. Webb's observations provide the evidence that our current map of the cosmos is incomplete. By revealing galaxies that shouldn't exist and an expansion rate we can't explain, the telescope is providing the raw data needed to build a more accurate version of reality.